Good. Yeah, so last time we saw what are regular functions, and they are elements of the coordinate ring, and they can be thought of as functions from x to k given by polynomials. And another way to think of it is so remember k is same as a1 sub k or a1, yeah, affine line. So so I mean it's another, so a1 is another name for k as a set in some sense, yeah. So you can also think of regular functions on x as morphisms of affine varieties from x to a1k. Yeah, so again, everywhere it should be affine. Yeah, so morphisms of affine varieties from x to a1. Because that is what our definition of morphism was. Morphism from x to y, a morphism between varieties is a function from x to y given by some polynomials, or more precisely, it's given by a ring homomorphism from a ring of regular from coordinate ring of y to coordinate ring of x. Yeah. So actually, I mean, if you give a regular function on x, which is same as giving a element of the coordinate ring, then it does define a morphism. Yeah, so this is equivalent to giving a morphism from x to a1k is equivalent to giving a k algebra homomorphism from the polynomial ring. So this is our polynomial ring. Kx to ring of regular functions, a coordinate ring of x. Yeah, and note that giving a k algebra homomorphism from polynomial ring is same as saying where does x go. Yeah, so you just have to say where does x go, and that determines the whole k algebra homomorphism. Yeah, so that is same as an element of Ox. So elements of Ox are in bijection with k algebra homomorphisms of from kx to Ox is in bijection with morphisms from x to a1k. So these are all same concepts. So there are many ways of thinking about regular functions. Yeah? Elements of the coordinate ring, or elements of or k algebra homomorphism from kx to ox, or morphism of affine varieties from x to a1k, and so on. Yeah. So bottom line, it is a function defined by polynomials. This is how one should think about it. Yeah? It's a function from x to k defined by polynomials in some sense. Okay. So for this reason, Ox is also called ring of regular functions on X. Yeah, because elements of Ox, which is the coordinate ring here, is the ring of is a ring, and it consists of all regular functions on X. Okay. Okay. So more, so this idea you can extend a little bit more. So more generally, if you are given m regular functions on X, then you can it defines a map from x to amk. Yeah, instead of one regular function, you get a map from x to a1. If you are m regular function, then you get a map from, I mean, amk is nothing but k power m. Yeah, so you'll get each basically a going to a point a in, or maybe I'm using p in the later half of the lecture. So p going to F1P to FMP. Okay, so P is some point in X. Okay. I mean, so why is this a morphism? Because you define you basically, to define a morphism, you have to give a map in the other direction at the level of coordinate ring. Yeah, and the map at the coordinate ring is given by this. And if yi going to fi, so once you declare where these variables go, y1 to yn, then that defines a unique K-algebra homomorphism from the polynomial ring K y1 to yn to Ox. And then you can verify that this does define this ring homomorphism, this K-algebra homomorphism, the map you get. So you know how the map goes, yeah? So given this ring homomorphism, if you want to define so given this ring homomorphism, you want to define this set map. You think of these sets X as set of maximal ideals of OX, and you just evaluate go Fi mod that maximal ideal to so you look at Fi, you look at so you pull back the maximal ideal, yeah. So and that is the map. Okay, so you have some maximal ideal here. You look at its pre-image, and you'll get this map. Okay, so you can verify this. So maybe I'll do it in a bit once I talk about M-spec and stuff. Okay. But this indeed gives you this this map. So that I should have done here as well. Yeah. So yeah, or maybe let me do this. Yeah. Okay, there is space here. So let me just do this. So we want to show that this ring homomorphism does induce this set map. Yeah. So let's let P be a point in X. Then that means we think of P as a maximal ideal. I P is a maximal ideal of OX, of this coordinate ring of X. And what is F hash inverse of this maximal ideal? Sorry, not P, but MP. P is the point. Let's denote by MP the maximal ideal of OX. Then what is F inverse of MP? F hash inverse of MP. So yeah, so yi goes to Fi. So so I want to say that this is exactly F1 evaluated at yeah. So I want to say, so the claim is that this so of course this is a maximal ideal because we are over, both are finitely generated K algebra. So maximal ideal pull back to maximal ideal, that is Hilbert-Null stanza, but we want to say exactly what this maximal ideal. So the claim is this is, so I think we did this, yeah. This argument we did. So the claim is that this is same as y1 minus f1p to ym minus fmp. So that is what one has to show. Yeah. So we have to show that y1 minus f1p belongs to this this maximal f hash inverse of maximal mp. Yeah. So okay. So yeah. Yeah, so you go mod the maximal ideal. Yeah? So f hash is this map. So I'll just show it for one. Yeah, so k y1 to ym to ox to ox mod mp. Okay, and so where does y1 go? Y1 goes to f1, and f1 goes to f1 mod mp. Yeah, mod this maximal ideal. And this is some element of, so this is the maximal ideal, and since we are over an algebraically closed field, this is going to be same as k, some element of k. Yeah. So this is precisely f1 evaluated at p. Yeah. If you evaluate f1 at p, and because you look at yeah, so I'll have to fix coordinates here. Yeah, so then it will work out. So yeah, so one has to fix coordinates. Kx1 to xn. So this you have to think of it as kx1 to xn mod p mod some prime ideal q, and then f1 you have to lift it here and do it. Yeah, so we did this last when we were trying to give this equivalence. Yeah, so I'll just, and then we realized that f1 mod mp is same as f1 evaluated at p. Okay, so this is same as f1 evaluated at p. So this tells us that so y1 goes to f1p, so that will tell you that y1 minus f1p will map to, this is an element of the field, will map to 0 under this composition, which implies that y1 minus f1p belongs to the kernel of this composition, which is f hash inverse of mp. Yeah, the kernel of this composition is inverse image of mp. Yeah, because kernel of this guy is of this map is mp, and then if you want to look at the kernel whole thing, then, and the same thing you can do with the others similarly for I greater equal to. So you get that so hence you get the claim. Okay, so so that tells you that this is indeed the ring homomorphism which defines this this map. Okay. So now, okay. So there is a slightly more general notion which is called rational function on an affine variety. Okay, so we'll talk about that. So regular functions are in particular a rational function, but rational functions may not be defined. So it's a function which may not be defined on whole of x. Yeah. So, but the easiest way to say what a rational function on a affine variety x is that it's an element of the field of fractions of the coordinate ring. Okay. So you look at the coordinate ring of x, and you look at its fraction field. So you take any element of that, and that's a rational function. So of course, every regular function is a rational function because coordinate ring contains is contained in the field of fraction. So one thing to note here is that here we really need a, so regular function you could have defined on any affine algebraic set, because you just say it's an element of element of the coordinate ring. And remember, coordinate ring we define for any affine algebraic set. Yeah. But for rational function, at least in this definition, we need it to be a variety so that we can talk about fraction field. Okay. But there is the other definition which we'll do works slightly more generally. So, but anyway, we are not going to discuss. We are not discussing things which are. So we are discussing affine algebraic set, but we won't discuss much about rational functions on them. Yeah. So, by the way, this fraction field, the field of fractions of OX, is also called the function field of X, because it's a field and it contains functions on X. I mean, the functions may not be defined on whole of X, but still, it's partially defined functions on X, and is denoted by K round bracket X. So remember, OX is also denoted by K square bracket X. Yeah, another notation for this guy is this guy is yeah, what has happened? Is K square bracket X. So we'll use this notation sort of interchangeably. So hopefully no one gets confused. Yeah, I mean, and in the books also you'll see various notations. So it's better to be familiar with the notations as well. Okay, so let's see an example. Yeah, so consider X to be the affine 2 space. Yeah. Then the coordinate ring we know is the polynomial ring in 2 variables, x1 and x2, over the field K, and then the field of fractions or the function field of X is fraction field, which is denoted by K round bracket x1 x2. So it's just the fraction field of the polynomial ring in 2 variables. So of course, if you take anything in the polynomial ring in 2 variables, you get a regular function on X, and it will define so I mean, it's a polynomial in 2 variables. So of course, it defines a function from A2 to K. Yeah, you just plug in two numbers from K, and you get you evaluate the polynomial, the first few functions which we see in our life. Yeah. But then we also see functions like this, x1 over x2. So these then of course these functions are not defined on whole of the plane. Yeah. When we realize, so these are rational functions, we say that it's not defined when x2 is 0. Yeah. But we still study these functions. These are nice functions. We try to graph them and so on. In BMath, sometimes they ask you to graph such functions. Yeah. So they are not a function. It's not a function on whole of X, but it still makes sense. Let's say away from x2 equals 0. Yeah. So F at least makes sense away from this set, A2 minus x2 equals 0. So if you want to picture it, you picture it R2 minus the y-axis, minus the x2 equals 0 means so x1 x minus the x1 axis. X2 equals 0 means x1 axis. Okay, to K, and then this function makes sense, because then x2 is not 0 on this set, and then this fraction makes sense. Okay. So we will see that so a rational function, another way to interpret it is a regular function on a non-empty open affine, at the moment, let's say affine subset of or non-empty open subset of X. Yeah. So it's a function which is so, but I want to say regular. Yeah. So it has to be variety. Yeah. So affine variety. Yeah, it's okay. So it's a subset, but it also has a variety structure. So maybe. So I mean, for instance, you think about this in this example, at least you look at this guy, A2 minus x2 equals 0. Then this is an affine variety. So I mean, you can think of it as with coordinate ring this guy, because so you can embed this A2 minus x2 equals 0. So you know, it's you're removing the x1 axis. So it's sort of you can't embed it in A2 as a closed subset, but in A3 you can embed it. Yeah. So its coordinate range is kx1 x2 1 over x2. So you can give a homeomorphism from this surface, which is in 3 space, to A2 minus x2 equals 0. You just project onto the first two components. Yeah. So that is the homeomorphism. And so what is an affine variety? It's a topological space together with some regular ring of regular functions, such that you know. So I mean, so the topology is just so it's a topological space, yeah, together with some so that we can think of it as closed subset V of some prime ideal. And x2, x3 minus 1 is indeed a prime ideal. It's an irreducible element of this thing. So we'll talk about this a little more rigorously, maybe in the next lecture. Okay, but that's what rational functions are. It's a function defined on some non-empty open subset of x. Okay. Function and it should again be given by some polynomial. Yeah, so once it's a function. So or more generally, it's a function defined by given by a rational function. So these are also called rational functions, if you like. I mean, these are not polynomials, but rational polynomials, ratios of two polynomials. So that's how the name, etc., comes in. This is how people were talking about these kind of functions. So again, more generally, so this is a rational function, and if you want to talk about a rational map, so more generally, a rational map for an affine variety x to an affine variety y is a morphism from a non-empty affine open subset of x to y, and it is denoted by f from x to y. So we have morphisms of variety. So sometimes it may not be easy to give a morphism of variety from x to y. You may just be able to give a rational map. So rational map is somewhat weaker than a morphism. So it may not be defined on whole of x, but maybe some affine open subset of non-empty affine open subset of x. So this word non-empty is very important. Yeah. Otherwise, you can always find. Yeah. So non-empty is, and another thing to notice is that now, as soon as you take a non-empty affine open subset of x, then it's automatically dense. Yeah. So maybe we'll discuss this. Let me just finish this bullet. So like in the regular function case, if you are given m rational functions on an affine variety, then they define a rational map from x to am. Yeah, because you just throw away the locus where you know, f1 to fm, they vanish. So you and then you get and then so f1 equals 0 is some set which is a closed subset. F2 equals 0 is some closed subset. You take the union of these is still a closed subset. You remove that away. Yeah. So what you get is you have removed a proper closed subset of x. So you get a open non-empty open subset. If you throw that away, you get a non-empty open subset of x, and hence you get and on that these f1 to fm does define a morphism. It does define a regular function. Yeah. On that open subset, and hence they define a morphism from that open subset to y to am. Yeah. Here I mean f1 to fm will define so f1 will define a rational function from x to k, which is a1k. So that's how you get a map from x to mk. Does that make sense, guys? so far? Any questions or comments? So the difference between rational function and regular function is just that the rational function may mean rational function's domain may not be whole of X. Yeah, it is some open dense subset, but it's almost whole of X. Yeah, what you're missing is a very small subset. Okay. And then like regular functions somehow defines morphism from X to A1 or AM if you have M regular functions. Rational functions defines rational map from X to AM because it's not uh, this function is not defined on whole of X, it's defined on some open subset. Yeah, so that's why it's not a regular, it's a morphism from X to M, it's just a rational map. Okay. So yeah, let's see why is every non-empty open subset of an affine variety dense in the Zariski topology. So here, of course, whenever we talk about open, dense, etc., we are looking at the Zariski topology. So why is it dense? So so let's say U contained in X is open, non-empty, empty subset. So affine is not, open non-empty subset of non-empty subset, and X is a variety, and X is affine variety. So why is it dense? So what does that? What does dense mean? So we would like to show that U closure of U is whole of X. Yeah. Are you guys still with me? Yeah. So how do you show closure of U is whole of X? Or I don't know. Yeah. So maybe that is what dense mean. Yeah. That is the so maybe this is the way to go about it. So why is U closure whole of X? So how do you compute U closure? What is the recipe? How do you compute closure of some subset of a affine variety?
Any closed subset containing U must be X.
Yeah,
Will
so
that
if
work?
you want to take a closed subset of X which contains U, it has to be X, yeah. Um, so so why is that? So why is U closure whole of X? So I mean, one has to work with something, yeah. So we maybe I don't know. We think of X as um, V of something, yeah. Z of a zero set of something, zero set of some prime ideal P, P contained in K x1 to xn, some prime ideal, yeah. So So how do you, and U is some open subset of X. Yeah. So what does, how do you compute U closure? So I don't know, maybe. So so if I give you a subset S, maybe some subset. Sorry. Um, uh, some subset. Yeah, let's call it as S in A and K. Yeah. So this I'm sure we have. I think I'm fairly positive that we have thought about. Yeah. So if I give you some subset S of An and I want to compute S closure, how do you do it? It is. So you want to compute the smallest closed subset containing S, yeah? So uh, so I mean you have to.
But the ideal generated by.
Yeah. So you take the ideal of definition of S, yeah? So you take ideal of definition of S, which by definition is f in the polynomial ring kx1 to xn, yeah, such that f of s is f of little s is 0 for all little s in capital S. Yeah, this is what ideal of definition is. Yeah. So S closure is not this. You just look at IS is this, and then S closure is just Z of IS. Yeah. This is how you get S closure. Yeah. So similarly, U closure will be same thing. Instead of looking at coordinate ring of the affine space, you have to look at the coordinate ring of X. Yeah. So you take F in OX such that F of um, F of P is 0 for all P in U. So P, same P. So let's just call this something else. Yeah, F of a point, maybe little p. 0 for all P in U. Okay.
Sir,
Mhm.
X is irreducible. So if U closure is smaller than X, then U bar and X minus U, that is a
Yeah. So maybe that is also, yeah. So maybe that's a smaller proof. Yeah. So X is irreducible. One can use that. Yeah. So X is irreducible. Then U closure. If this is properly contained in X, then this is closed. Yeah, that's probably a better way. Otherwise, we would have to do some commutative algebra. And X minus U. Yeah, so this of course contains U. So X minus U is closed, and this is also proper. So closed and uh, different from X. And X equals X minus U union U closure. Yeah. So that tells you that contradicting X's, contradicting X's. irreducible. Yeah. So otherwise, I mean, we'll trace down the proof of why irreducible if and only if p prime kind of argument will come in. Okay. The way I was going. Yeah. So this is probably more efficient. Okay. So as you can see, variety is important. Yeah. Because if I give you any algebraic set, for instance, I can take 2 points. Yeah. Then of course. This a singleton point is a open subset as well. It's closed and open, and it will not be dense. Yeah, so you can just take something disconnected. So variety is important for this statement. Okay. Any questions or comments so far? Okay, so let me. So we also want to think of in terms of maximal ideal. So X, you can also think of it as n spec of some R, yeah. And when where R is some K algebra, and when K is algebraically closed, then we know that maximal ideals and are in bijection with points of X in some sense. Yeah, if you embed X in some affine space, you can do this more explicitly. So now if you are given f in R, the function defined by f from X to K is, so if you think of X as m spec R, how do you define the function from X to, and f is a rational, f is a regular function. So since f is an element of R, f is a regular function of from X to K. Yeah. So how do you define f from so how does this regular function define function from X to K? So what is the I have to thicken this. So what is the function we get? What is this map? So where should the maximal ideal go to? M is some maximal. So now points of X, we are thinking of it as maximal ideals of R. So where should this maximal ideal go to? Which element of K?
The coordinate ring by M. Sorry.
So the image of F under the map R mod M, yeah? So
yes.
F, let's say F mod M. So we have a map from R to R mod M, and F goes to F mod M in this sense. This is what F mod M means. Yeah. So this is how you think of yeah. So if you are thinking in terms of maximal ideals, X. So so the advantages of thinking, because then the map sort of becomes easier to think about. You can so this is how you would want to translate from algebra to geometry and vice versa. So you should think of X both in terms of maximal ideals as well as points. Yeah. And I mean, even when you are working over algebraically closed field, this gives you some added advantage. Yeah. And of course, if you're not working over algebraically closed field, there is no other way to think about it. But the pictures always come from algebraically closed field in some sense. Yeah. Just that the plotting is done over, everything is done over reals, but so that the dimensions don't go up very fast. But we should have all the interpretations at our hand. Okay. So, okay. So now if you are given a rational function on a variety x, then f as we know is not defined on whole of x, but is defined on most points of x, at least in the examples we have seen. So we will in fact show that the domain of f is in fact an affine open, is an open dense subset of x. Yeah. So f is said to be regular at a point p in x if f makes sense at that point. In other words, there exists g and h in O. So f is a rational function, means it's an element of the fraction field of OX. Yeah. So f you can write it as g over h, and hp is non-zero. Yeah. So of course f you can write it as g over h in many ways, right? Because you just multiply something else both in the numerator and denominator, some non-zero element, and still you can it is the same guy. So if you can find some g over h such that hp is non-zero, then you say that f is regular at a point at that point p of x. Okay. So a rational function is regular at many points of the variety x. A regular function will be regular at every point. Yeah, because if it is regular, it's in the coordinate ring. You can always take h to be 1. Yeah, and that and p to be, and 1 never vanish at any point of x. So domain of a rational function is a set of all points of x where f is regular at p, such that f is regular at p. Yeah. So we have this proposition which says that the domain of, yeah, any questions? Okay. So so x, we say that x is so the first statement is that domain of f is an open dense subset of x. So we only have to show that is non-empty and open. Yeah, dense will follow as soon as we get non-empty. Domain of f is whole of x if and only if f is a regular function. So if f is regular, domain of f is x is trivial, and the converse also holds. Consequence of Hilbert-Nernst turns up, and then domain of f contains these are called some basic open sets. Yeah, x sub h, which by definition is those points of x where hp is non-zero for some and these are defined for h element of the regular h a regular function. So if h is some regular function on x, then you define xh as those points of x where h does not vanish. Okay. So domain of f contains x sub h if and only if f belongs to this subring of the fraction field. Yeah, so you should think of this as subring of the fraction field, field of functions of x. Yeah. So, so these statements are not very difficult. So we will see the proof, and yeah, so I've given the proof here. So yeah. So let's see the proof. So the statements are here. So first thing we want to show is that the domain of f of a rational function is an open dense subset of x. So let's take f to be a rational function, and kx, which is the coordinate ring of x, which also is denoted by ox. So you define I to be this colon ideal. Yeah. So remember we talked about this a little briefly. So it's by definition is those elements of kx of the coordinate ring such that g times f belongs to the coordinate ring. Yeah. So f is some rational function. Yeah. So you want to take those elements of the coordinate ring such that when you multiply with f, you land in the coordinate. So for instance, 1 may not belong to this ideal I, because if f is not in the coordinate ring, then 1 will not belong to. In fact, 1 will belong to this if and only if f belongs to kx. Yeah. So this we saw when we were doing primary decomposition, this kind of construction, primary ideals and so on. So first thing to note is that this is indeed a non-zero ideal of OX. Yeah, because I don't know why is this a non. So first of all, why is this an ideal? So if G is there and H is there, then of course G times F belongs to Kx and H times F belongs to Kx. So G plus H times F belongs to Kx. G plus H whole times F belongs to Kx. Yeah. So it is, and even if G belongs to Kx and R is an element of Kx, then G belongs to I and R is an element of Kx, then of course G times F belongs to Kx. So R times G times F belongs to Kx. So that tells you that R times G belongs to I. Yeah. So this is trivially an ideal. And why is it non-zero? So what's one non-zero element you can find? So it will depend upon F, yeah. So F is a rational function, yeah. So F is some I don't know, F1 over F2, where F1, F2 are in Kx, and F2 is non-zero. Regular functions, yeah, and F2 is non-zero. So which element do you think is in I?
F2 is,
Then F2, yeah. So if you multiply by F2, you land in Kx, yeah. So then F2 belongs to I. So there are non-zero elements in I, yeah. So I is a non-zero ideal. So now if we prove this claim that P belongs to Vi if and only if P is not regular at P, then Vi is same as Zi. Sorry. So okay. So I'll just stick to Vi. Yeah. So then Vi is a proper closed subset of X. Yeah. So its complement is an open. Since I is a non-zero ideal, Vi is a proper closed subset. Yeah. So that I mean that of course. As soon as you take some non-zero ideal, you get some proper closed subset. Yeah. Since we are over a variety. So and hence we'll conclude that domain of F is an open non-empty open subset of X. Yeah. So this claim implies one. So maybe claim implies one since I not equal to 0 implies Vi is not is a closed subset of X and is a proper closed subset of X. Yeah. Okay, so let's just prove this claim. So suppose F so which direction am I proving? Yeah, so suppose F is F, so suppose F is regular. Yeah, so let's assume P belongs to forward direction. Okay. So forward direction. So suppose so P belongs to Vi. We want to show that F is not regular at P. So suppose F is G over H. So assume F is regular, and we'll get some contradiction. So suppose F is G over H with G H a regular function on X, and HP is non-zero. But H belongs to Vi, yeah, because F is G over H, then H times F is a regular function, so H belongs to Vi, yeah, since HF belongs to Kx. Yeah. So H belongs to Vi. That is the definition of I. Yeah. And no, not Vi, but H belongs to I is what I want to say. Not Vi. But H belongs to I. So, but since H belongs to I and P belongs to Vi, HP must be 0. Yeah. Since P belongs to Vi. So HP must be 0, which contradicts our assumption. So that tells you that F is not regular at P. Yeah. Conversely, if F is not regular at P and H belongs to the ideal I, then we want to show that H of P is 0. Yeah, that we want to show that P belongs to Vi means any arbitrary element we take of I, then H of H, and then that element vanishes at P. Yeah. So now if F is not regular at P, then what does and H belongs to I, then if H belongs to I, HF of course belongs to Kx, yeah, and HF let's call it G, because that's the definition of I, it's the colon ideal, yeah. So HF belongs to Kx, which is G, and um, uh, and that means that F is G over H, yeah. So F is G over H, but F is not regular at P, that means H of P has to be 0, yeah. Since F is G over H and F is not regular at P. Because if HP is non-zero, then we have found, we have written F as G over H and HP is non-zero. So that tells you that given any point P, which is where F is not regular, then P has to belong to V of this ideal which we defined. Okay. So this ideal is defined to make sure. So this is the indeterminacy locus of this F, where it vanishes. So it's basically ideal generated by a collection of denominators of F. So F may be expressed in as something over something in many different ways. You just consider the ideal generated by all the denominators. That's what I is. Yeah. And then of course V of I will be precisely where F doesn't make sense. Yeah. And once we realize that that is a non-zero ideal, then that's it. Okay, so that completes the proof of 1. And for 2, so domain of so of course, if F is regular, domain of X is domain of F is whole of X, and if domain of F is equal to X, yeah, then what does that mean? So this means that so we have if we take let I be this colon ideal. Kx colon F, then what we know is that V of I is, so V of I is the indeterminacy locus, the locus where F is non-defined. So we know that V of I is empty, yeah. If the domain of X is whole, the domain of F is whole of X, then V of I is empty, and this is by Hilbert-Null's term. So this was one of the consequences of Hilbert-Null's tensors. This precisely means that I is the whole ring. Kx. Okay. So yeah, maybe I should say a little, since I mean we saw it in terms of polynomial ring. Yeah. So maybe I'll say a little more about it. Yeah. So yeah. So x is V of P, where P is some prime ideal in kx1 to xn, kx1 to xn, yeah, and yeah. So how do I say this? Yeah, and so kx is kx1 to xn mod p. So all this statement which we have, for this one which we showed that if we have an here k is algebraically closed, yeah. Otherwise, I mean, affine varieties we have defined only in this case, yeah. Otherwise, we have to take maximal ideals, and again the same. Again, it works out, yeah. So if your definition of V of I or X is M spec of the coordinate ring of X, then also this works out, yeah. So maybe some parts I'll leave it as homework. So this is this guy, okay, and yeah. So I is some ideal in Kx. Then this is in one-to-one bijection with an ideal I tilde of in kx1 to xn containing P. Okay, and V of I is a closed subset of X. Yeah, so V of I, you can think of it is same as V. So V of I contained in X contained in An. If you use this this interpretation of Kx is same as V of I tilde. Yeah. So now for this we had seen that if for this polynomial ring we had seen that if V of I tilde is empty implies um, um, I tilde is kx1 to xn. Yeah, and if I tilde is kx1 to xn, this implies I has to be kx, coordinate ring of x. Okay. So basically, I tilde is the intersection of all maximal ideals. If you are looking in terms of maximal ideals, so and otherwise, if I tilde is a proper ideal, then of course you can find a maximal ideal containing I tilde, and then that maximal ideal is going to be of the form x1 minus a1 to x1 xn minus an for some a1 to an, because K is a algebraically closed field by Hilbert-Stanza, and that tells you that a1 to an will belong to V of I tilde. Yeah. So that is how the proof goes using Hilbert-Stanza. Okay, so I hope this is clear. I've chased down how it follows from the elementary version of Hilbert-Stanza. Okay, and maybe 3 is somewhat similar. So I'll just leave 3 as a exercise or a homework, depending upon how long. Yeah, so this is also sort of Hilbert-Stanza, but the radical version of it. Yeah. So and that will be a homework. So maybe this is a good place to stop. So, something went wrong. Okay. Okay. So screens sharing has stopped automatically. I don't know why, but I hope the video has